All right. All right, everybody. Hello and welcome to the stream. Today is January 23rd, 2020. It's 12:19 in the afternoon. A little bit late, just like always. Um, Today, I want to start off by showing you something that I did recently, which was on my website. New. One of these. I added this new mentorship section, which is awesome. Right now it only has 2 questions in it. I have gotten the okay from a few more people to add some stuff in here. I just haven't had the time to do that. We're going to do one of those today. Hey, what's up? How are you? And then after we get done adding this in here, we're going to get back on what we were doing, which is looking at the reinforcement learning stuff and PyTorch and seeing if we can actually toss in... Oh wait, I gotta get off of Slay the Spire. Damn, I never edit my stream info. It's not even Friday. It's Thursday. Mentoring stuff. Then PyTorch again. Slay the Spire. I wish there was a way to like make it no. Hey, wow, thank you so much. I really appreciate that. If you don't mind me asking, what was that for? Slay the Spire. Science and technology. Boom. Yeah, thank you so much. I really appreciate that. Okay, mentorship. Boom. Boom. There we go. I got a couple of questions on here that I answered already. The way that these are going to work is people send me emails that have questions, or they'll send me like a DM on Twitter or wherever, and it includes a bunch of questions. And so what I do is I actually post the questions that the people asked with their permission. If I change the name, if they want me to change the name. And then after that, I actually respond to each one of it. And that's how these are going to work. So ideally, what I want you to get out of this is that these are real questions. Like, these are the kinds of questions when somebody is looking for mentorship that they might ask, and this is the kind of answer that I might give. It's not like, here's some code, can you solve this code for me all the time? A lot of these questions are about like the industry at large, or they're about, you know, one thing or another. And so we go into a lot of different topics. And like I said, I've got a bunch of them to do. Right now, I want to get one more in there from somebody who I was helping the other day. And this is what the question was. Let's go ahead and pull up... No, I don't want to do that. Let's go ahead and pull up VS Code. And we'll just add a new one altogether. Open recent. Nope. Cancel. File, open recent. That one. Yeah, sure, save that. All right. And then right here, get a hexo, new mentorship. And then we're going to call this one. So this is, I'm a computer science student and currently in the middle of the course. I've been thinking a lot about my future, and since computer science is a really broad field, I have to say that I'm a little confused about which path I should pursue. Everywhere I'm seeing that machine learning, deep learning is a growing field with lots of opportunity. Okay. What's a good path for the future? I use Hexo as my static site generator. It's been mostly good. There's a few things that are frustrating about it, but I think those have more to do with Jekyll. What's a good way? Okay, let's rename this. Rename. Because I don't want that. Alright, what's a good path for the future? Tags. I don't have tags. Why did this come through like this? Oh, it's because I did it on the other machine. I gotta pull. Pull. Yeah, how are y'all doing today? The UI here for telling whether or not it's actually pulling is not super great. Tasks, extensions, Git. There we go. Please clean the repository working tree before a checkout. That sucks. So it seems to think that I made changes to all of these things. No. Can I do it now? Was it just that I had the editor open? No. Okay, so we're going to close that. We're going to open that. And we're going to do it with a GUI. If I can find it. Culture of development, GitHub, open. Okay, pull all. Oh, it's because I was trying to get the WASM stuff done. That's what it is. Sure, so let's just reset all of this. And that was the thing that I was disliking about it. The whole like Jekyll thing not allowing reset for real. Okay. Now pull. What? Merge. There we go. Okay, one more time. So, oh, it's been way too easy. Extensions have been modified on disk. Please reload. Hexo new. Hey, Clarkio, thanks so much, man. Welcome, everybody. Please tell me what y'all were working on today. Fake answers only, please. Working on Microsoft Docs top navigation today. Oh, I think I know who you are. More comments, less code. All right, what are we working on? Two things today. The first one is I added a new section to my website about mentorship where I ask people who I mentor if they're willing to let me post the questions from what they asked me onto my website. I added a new section to it, and we're going to add one right now, and then after that we're going to bounce back over and get back to work on some reinforcement learning stuff that I'm trying to learn. And it's going to be fun. So conceptually, the reinforcement learning stuff is to mimic some research that's already out there. Hey, what is up, man? How are you doing, Courtney? Or is it Court? Do you prefer Court? Also, thanks for stopping by. And so let's just get this. So the question that this person is asking is about what's a good thing to learn right now? What's a good thing to learn right now? to prepare me for the future? And I actually really liked this question. I also really like my response, so I'm going to get both of these in here for you. Now let's scroll down. Hey, there we go. Okay, see, now it's in the correct format. That's what I was expecting. Rename. We're not going to do any video on this one, and this question was from January 15th. So we're going to change the date to the 15th. All right, what's a good thing to learn right now to prepare me for the future? And then let's go like this. All right, here is the question in full. Are you answering that, or are we? No, I answered the question. So this is the actual question that the person sent to me. They said I could share it. And then I sent them a response, and I'll get to that in just a moment. But then you can tell me whether or not you agree with what I said, and maybe we can make it even better. So the question is, I'm a computer science student currently in the middle of the course. I've been thinking a lot about my future career, and since computer science is a really broad field, I have to say that I'm a little confused about which path I should pursue. Everywhere, I'm seeing that machine deep learning is a growing field with lots of good opportunities, and in my university, there are a lot of research being made in the field. One of my professors called me to participate in one, so that's the path that I'm thinking about right now. One of the concerns that I have is the fact that there are so many people studying the field. I'm always thinking maybe in the near future there will be so many AI people and not as many jobs out there. Could you give me your opinion as someone with a lot of experience on the industry? I would like to know from someone more knowledgeable if I'm really making a good choice focusing my effort on it. Well, having said all this, my objective trying to find someone to mentor me is to have some guidance to my studies. I have no problem studying by myself, but I always starting and stopping, and maybe I'm not good at establishing short-term objectives. There's a lot to discuss here for sure, but I think that's enough for now. Thank you very much for your attention. By the way, if you have... Oh, if you're too occupied, we'll get rid of that one. We don't need that in there. Willing to answer. We also don't need that one in there. Okay, best regards. My response was as follows. Ooh. Boom. All this text. In this case, the grammar's not that bad. If there was something like super egregious, I would probably fix it. But in this case, there were a couple of words that sounded misplaced. But I'm not going to worry about that. I think it's more okay to show what people are actually asking. Like, I'm not an editor per se on this. All right. I'm happy to, so dear Luan, I'm happy to help you stay motivated and keep moving on your studies. I love AI and ML, and it's awesome that you're interested in it. But before we go that route, let's talk about your concerns. Everything is just hype, as you will see time and time again. In not just our industry, but also in just about every industry, people need to be excited about stuff in order to invest in it. So the hype machine gets started, and everyone who wants some money to pursue their dreams jumps on that train and perpetuates the vision. Take, for example, self-driving cars. I absolutely love this idea. It solves way more problems than it creates, in my opinion. And it has the potential to make the world an enormously safer place to live for everyone. There were significant advances made in this space, and it got to the point where even major car manufacturers were declaring they would have consumer-ready self-driving cars available in 3 years. That was promised as far back as 2016. Obviously, that didn't happen. It was just a really good story, and the hype train was having a giant party on board. Turns out driving cars is constantly seeing new situation, and our existing methods for training models do not handle unseen conditions even good enough to go to market. It's a super hard problem. The world is full of these hard problems, and while AI and ML seem promising to make advances in these areas, it's nothing more than hype until someone actually does it. Will there be less jobs out there? I'm not so sure about that. And these are just my ideas, but it seems unlikely that the jobs will dry up anytime in the next decade, barring artificial general intelligence coming to fruition, which is essentially consensus that won't happen. I think of AI and ML just like I think of sorting and searching. They're just problem solving techniques. You got a problem where you need to locate a user record in a database, you use searching. You need to organize a list from most important to least, you sort it. You need to find directions on a map, you use AI. You need to predict the price of a house, you use ML. It turns out there are a lot more interesting problems that, oh look, see I have a typo, that AI and ML can be used for that they haven't been applied to yet. I think in the near future, AI and ML knowledge will be required for far more positions. You won't be a data scientist because you know it. You'll still just be a developer, but those kinds of techniques will be necessary to keep your solutions on par with the rest of the industry. It's just a new button on your calculator. All right. I also see professional certifications becoming a requirement for specific job roles in CS, a lot like lawyers have to pass the bar and how doctors can pursue a board certification. There are a lot of ethics concerns in the problems that we are applying AI and ML to, more so ML, as well as a lot of common mistakes which invalidate the science aspect of the work, and having a professional certification seems like the most natural way for practitioners to convince people of their skills. You will need something like this for, or will you need something like this for making web apps? No, of course not. But for the jobs where you can create an enormous amount of ill, it's long overdue. Programming to me is just a really fancy calculator. It's not that useful on its own, but it can save you enormous amounts of effort when you use it to help you solve other problems, which brings us back to your first question. Which field should you pursue? The answer is simple. Try them all. Choose the one you enjoy the best. Don't worry about your future prospects. Your long-term happiness depends on enjoying the work you do. Despite what people say, you don't even need to be passionate about the things you do. You just need to feel like your work has purpose, and that will be enough. Go find your purpose. Try as many things as you can right now and figure out what problems you want to solve. Then just try to solve them. When you're focused on solving a problem, you'll learn whatever you need to in order to solve that problem, and you won't feel like you're limited to being an ML dev or a web dev or whatever. You'll just constantly learn new techniques to apply to your problem every day until you stop making progress. Then you'll go learn some more. All right, I'm happy to answer any other specific questions you have about the industry, some ideas about problems you might want to work on, or I can help you further understand the techniques you are currently learning. Feel free to ask anything. That's it. That's my response. Do you feel like that appropriately addresses the questions here? It's hard to condense down a lot of what's being asked into like a couple of paragraphs for me. It's like I think back time and time again about the stuff that has happened to me, like in my industry and my career, you know, with other projects that I've worked on. And it's like, yes, this thing would have been helpful. This thing would not have been helpful. I don't know if it would be helpful for you, but I just try to give you my view on things. Anyway, let's get it checked in. Hexo generate, nope, deploy, generate. And that's it. That's how long it takes. So, oh, that looked like an error. That definitely looked like an error. Let's see if we can scroll back up. Okay, cannot read property data of undefined. Did I not check that in? Mentorship email. Maybe I need to hexo update. Data. Oh, that's not good. Let's go. Do 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 do. I don't even want this in here. Othello Blazer Wasm. You can delete that. Source. This needs to be deleted. I think that was actually the cause of the problem. There's an HTML file in there, and I think it was taking that HTML file. You are attacking AI, but maybe ignore that he's asking about AI and talk more about your amazing comment of try everything. How am I attacking AI? I'm not sure I understand that fully. But the try everything, yeah. Do try everything. Like the thing, this goes back to like your reason. AI isn't cool. I love AI and ML, and it's awesome that you're interested in it. Oh, everything is just hype. I don't know. How could I have said it better? Try everything. Yeah, try everything. I feel like almost everybody gets started with programming for... Skip talking about AI. Okay, that's fair. I feel like everybody gets started with programming because something comes along and they're like, I want to do that, right? Whether it's like, oh, I want a website that does this, and then so they sit down and they try to make a thing. Or whether they're like, oh, I played this video game and I really want to like make a video game, so they sit down and they like learn some whatever. And normally these things are really big and really grandiose, and when you get into it, you're like, oh my goodness, that would take half my life. But that's the thing, is like sometimes it is so powerful that you're like willing to devote some amount of your life to it. And that is when you know you have found the thing, right? That's when you know whatever you do, it's going to make you happy when you're working on this thing. And for me, that was, I started out making games, and then I learned web development just by chance, and I got super interested in that. Prior to there being a Facebook, I had created a like page, a website a lot like Facebook, for my friend group in high school, where you could like post about each other, and you could like put things on there about what you had done and whatnot. You could post pictures, and then we had a bunch of really funny stuff too, where we had this page about the dictionary of words that we use, which is like sort of like what's that big one now? Urban Dictionary. But it was like words that just our friends used. And like to be able to provide those things and like have people enjoy that, and like it just made us all tighter as a group. Every once in a while we'd be sitting around in the basement, you go back and you like look at the past things that you've done. It was so much fun, right? And that's what got me so hooked on it. And then I got into college and I took a class on AI, and it was a really, really intro level basic AI. You took like the big green book, and then you went through and you did like, I don't know, 8 or 10 of the chapters, and that was the whole class. But I remember in that getting to the point where I could get a car to drive in a grid world from like one location to another location consistently and in the most optimal way. And like then I went and I learned how to do Minimax, and I started writing like tic-tac-toe games and really interesting stuff like that, and that's when I got super hooked on that stuff. And then by the time I had graduated college, I had actually built up to making a poker playing robot, which was absolutely the most amount of work I had ever put into anything up to that point. And it's like that was the thing where I knew that was what I was always going to come back to. And that's like on stream, that's what I do. That's what we're going to do right after this. And I don't get to use that kind of stuff at work anymore, but I learn the stuff that I need in order to be able to do that. I try to apply it to work where I can, but like that's the thing that keeps me super motivated about it. Like I am not like passionate about the work that I do. It's a good job and I really enjoy it. It pays my bills, it gives my family a nice living, but at the end of the day, when I get off of work, I like sit down and this is the stuff that I do. I write these sorts of bots and I write these sorts of game playing things and I write these tools that will go through and simulate different things to help me learn how to be better at this boss fight or this whatever. And that's the thing I always come back to. I've learned so much stuff in order to be able to like do better and better and better at that, and that's it. I mean, that was my try everything. That's my path. What kind of stuff have you done? Web, yeah. What kind of stuff on the web? There's lots of stuff. Okay. Feel free to ask anything. I'm happy to answer specific questions. I wanted to hexo generate one more time, see if it's still going to crap out on me. It is still crapping out on me. I wonder if I can tell what page it's breaking on. It's trying to do files loaded. Cannot read property data of undefined. Huh. Weird. I wonder why it's doing that. Mentorship streams, no Jekyll. Index.html. It's this one. Okay, so that's what it is. I need to find that index.html. Or maybe... Oh. Okay, so if it doesn't have a category, so the home page doesn't have a category, so I need to make it... I love the web. I've been doing it for 20 years, and I keep loving it. Mainly front end. That's awesome. Front end becoming more and more complex. The front end is becoming more and more complex. Yeah, I remember God, when I first started doing front end stuff, it was like you learned HTML and CSS, and then JavaScript was like way too hard for me. Could not understand how like there was just stuff there without you writing it. I had such a hard time with that. I don't know why. It was so weird. Now there's frameworks and packages and you pull it all in and it's all super easy to get past that hump. But yeah, it was just like so mind blowing for me. And then there was jQuery and everything got easy for a while. And then I don't know what happened. Okay, let's just check to make sure in the theme source layout. What if we... Oh, look, there is index. Huh. What if we go to post and then we just check to make sure that it's in there before we try to use it? Right? So then let's say if page.categories and... Okay, let's see if that craps out. All right, that seems better. Perfect. And now it's deployed. Okay, let's commit this. Okay. Fix minor exception on post.ejs. Commit add mentorship the future. Push. And then let's just see. Hey, there it is. All right, perfect. All right, I think every day I want to try and add one of these because gotta have plenty of them in here. So we'll just come back here and try to add one each day. And y'all can do it with me and we can talk about them. There was IE to make our lives hard back then. Now it's the big battle of frameworks, which still prevents me from committing my time. Keeps me away from committing my time. Yeah. Okay, that's it for mentorship. Let's go to the next thing. AlphaZero. Take me to the paper. Okay. There it is. All right, so for those of you who are not familiar, there is this game-playing robot called AlphaZero, and the way that it works is it starts with no knowledge whatsoever of anything, period. And what they do is they then teach a single game-playing robot to play 3 different games, all at superhuman ability. And those 3 games are Go, chess, and shogi. And it's the exact same neural network, effectively, that plays all 3 games. And that's it. That's the whole thing, right? And so the way that it works under the hood is you have the neural network and you train this neural network to be able to give you a move distribution for whatever state you happen to be in at this time. Okay? So like in chess, you can move 10 different pieces, and you can move to, maybe there's 14 possible moves on your turn. And so what it does is it gives you a probability distribution over those 14 moves, and then you select one of them randomly with that distribution. And so that's what it is, right? And it works for all of these different games. It works for Go, it works for chess, and it works for this other game, shogi. Chess being the easiest of these 3 games. Okay? When it gives you a move distribution, we don't know that the value function that it has come up with is good or bad. So instead, what we do is we wrap this whole thing that gives you the move distribution inside of another algorithm called Monte Carlo tree search, and then we just use that to play out simulated games. Okay? So we have this thing where we are going to go and play, it becomes our turn, and we're going to go and play, like, say, 10,000 or 100,000, however many, maybe even less than that, maybe even just like 1,000 random games from the current state all the way until the end of the game, or some cut off at, like, say, 100 moves or something like that, because we're just not going to play past that. And then whatever the score ends up being, whether you won, whether you lost, we pop that stuff back up the tree. And then over time, it starts selecting the best move, even if our value function is wrong, right? And that's like the key trick of it is. We create the best possible, what's called a function evaluator, approximator. Basically, we come up with a policy that we think is the best way to play this game. And then even if we're wrong, we use Monte Carlo tree search to sort of help us figure that out as we go. Okay, so we train this thing, and then if we get stuck, we're just like, you know what? Let's just keep trying and keep trying. Okay, so previously, we have implemented the Monte Carlo tree search part of this. Let me go ahead and bring that up. File, open recent, Monte Carlo tree search. And we did it for a game called Othello. Just to show you how this works, I want to say I made it so that cd space src, and then I want to say .NET run. Hey, thank you so much for the follow, Pac-Man Jr. I really appreciate that. .NET run, and then what do we do? Project Othello. Othello Blazer. I think it's Othello Blazer. And what this is going to do is we basically built a web app that will play this game against us. And so far, I have not beaten it. And this is a really naive way to do this. But just so you can actually see, what number is it? 5001. HTTP s:// localhost. Oh, 5001. Whatever. Just do it. Do the unsafe thing. All right, so we go play Othello. If you're not familiar with this game, the way that it works, let me see if I can make this bigger. There we go. Okay, the way that this works is I am the red player, and you can play any place where one of these shadowy dots shows up by clicking on it, and the only way that it determines where you can play is that you must capture some of the opponent's pieces. So if I play a red piece here, then I surround it from edge to edge, meaning that I have one on the bottom and I have one on the top, so I can collect both of those. And then it makes its move. And it tells you it ran 1,000 simulations, and that's because it only runs simulations for 1 second. And then at the end of 1 second, it thinks it has a 56% chance of winning if it makes that move, so it makes that move. And that's it. That's how the whole thing works. This is the Monte Carlo simulation. It runs each of these over and over and over and over again. And then based on which one is doing the best, it normally chooses that one, but it has a little like penalty built into it so that it will always choose the other moves to some degree. Right? It won't constantly choose the same move if the first time it plays it won. Right? On the opposite side, and this was something that we actually ran into when we were developing this, was it also ran into this situation where if it lost the first game, it would never try that move again. Which was bad because if it randomly selected, the moves that led it to a loss, but that one really had like a 90% chance of winning, then it would just be like, nope, I think I lost, and it would never do that again. So adding in that penalty so that it constantly retries some of the older moves that it hasn't tried in a while is what makes it so powerful. And then I'll just play a little bit here so you can see how this gets to the end of a game. So now I can capture 2 pieces if I play right here because I can get both of these in the middle. And it's fun to watch it because it thinks it's doing better than me, and it probably is. Now it thinks I'm doing better than it. Notice that? It thinks it's going to lose now, or really what it thinks is that there is about a 50% chance of it winning. And it is possible to tie in this game as well. Ooh, see? Now it thinks it has a 55% chance, so it thinks I made a bad move. And now it has a 57% chance, it thinks. And you can see how this goes. And as we get deeper into the game, I'm going to start playing really fast here and not caring about whether I win or lost. Because I just want to show you that as we get deeper into the game, it actually does more simulations as it goes. And the way that it does that is that there are just fewer moves to roll out to get to the end of the game. So the key point here is that in order to evaluate a win or a loss, we need it to be really fast, so that we can consistently choose a lot of moves, and that's where the neural network comes in. The neural network comes in because we can simulate the entire game by just predicting the chance to win that game immediately. So I think people who are better practitioners with ML and neural networks would definitely like gawk at me saying this, but one of my favorite use cases for, and now it has a 90% chance, yeah. So I'm done. Okay. One of the absolute best use cases for a neural network is when you think to yourself, I want to remember that, and then I want to go retrieve it later. Right? It's just a very, very, very good tool for remembering a thing and being able to recall it later. Imagine if you put an image into it. Imagine it like this, right? There is a type of neural network called an autoencoder followed by a decoder. And if you train it on the input image to the same output, what it will do is it will take that input and it will take that image as input and it will try to generate that image as output. And if you train it enough times, it'll be able to do this for any number of images. And the real magic of this, not for any number, there is some limit to it, of course, but for all practicality, it can remember it. But the real trick and the real magic of this is that the parameters of your neural network are predefined and unchanging, meaning that you can put more pictures into it than you can get out. Or excuse me, you can put more pictures into it, more data than the size of the parameters, and it will be able to regenerate those on the output to some degree. Maybe not 100% perfect, but close enough for you to not be able to tell the difference. And that's really, really cool, right? Imagine if you had like terabytes of images and you shoved them all into a neural network that was trained to output the same image that you put into it. And then there was a way for us to, using something smaller, yeah, exactly, as a compression algorithm, exactly what I'm talking about. And then the trick to it is, in order to get something out of it, you now have to have a representation. But the trick of a neural network is, when you get to the point where you are just putting in and feeding out, you can now start cutting off the layers, right? You can say, take off the entire encoder and just give me the encoding for each of my images, which is going to be notably smaller than each of your images. If your image was, say, I don't know, 1,000 pixels by 1,000 pixels, I'm just pulling numbers out of a hat here, then your encoding layer, at the end of your encoding, might be as few as only a few hundred values. And those can be stored in like doubles or even floats, really. So yeah, you're talking like your image that was 1,000 by 1,000 times 300 could be compressed down into something that is literally on the order of bytes. And then as long as you have the correct decoder, you only need the decoding part to get back exactly the original image. So yes, it's effectively a compression algorithm. When we use it for games, there are way too many states in this game, too many possible states to remember all of them, and like, say, you know, creating a map and saying, think of it as like a dictionary, right? This is my input state. This is my expected value. This is my input state. This is my expected value. And we have way too many of those in order to be able to enumerate all of them for this game. So instead, what we're going to do is we're going to use a neural network. And we're going to say, when you see this state, I want this value on the output. When you see this state, I want this value on the output. When you see this state, I want this value on the output. And we're going to train it over and over and over and over and over so it learns this and can regenerate those values with a high degree of accuracy. And then what we're going to do is we're going to say, when I run into any state in my game, I am just going to predict the chance of winning that game directly, instead of actually simulating out an entire game. Now what I can do is I can say, okay, here is my state, and within a very well-defined amount of time, I can get back an exact evaluation of what my chance is to win, and then I can propagate that back up the tree. And then this total sims right here, instead of it getting better as it goes, it will be constant. So I can say run 10,000 simulations, and it will always take the same amount of time. And that's where we're trying to get to. And we're not going to get fully there today, but that's what we're working on. Cool. Any questions? I just got all, it's like hot in my office now. Oh. Okay. So this is the paper that describes that, and I just want to look over it a little bit to make sure that I'm describing it accurately. And then in addition to that, I want to pop back over to the PyTorch stuff that we were doing and see if we can put together a neural network that can do that. Because I don't know how to do it. They don't describe it in detail here. All right. The AlphaZero algorithm described in this paper differs from the original AlphaGo Zero algorithm in several aspects. So AlphaGo Zero played the game Go starting with no previous knowledge. Any questions? So many. This is super cool. Going to be a fun stream. Thanks. Yeah, if you have any questions, dude, just interrupt me. More than happy to answer them. So there was this tool called AlphaGo, and AlphaGo used a bunch of recorded human games as the original input to say this was a good move, this is a bad move, this is a good move, this is a bad move. And then it added that layer on top, and it literally was just that. It was literally, here is the input, and then here is whether they won or lost the game, and what percentage chance, you know, from this position ended in this sort of a thing. And they trained it from like millions and millions of recorded human games. And then they played some self-play to build additional ones where during the self-play they had that that Monte Carlo tree search like on top of it, so that the games that they were playing were taking into account that additional information that it had learned. And then they kept training it and training it and training it. And that game on its own reached a level that was better and ended up beating the top champion in Go. Then they changed algorithms and they said, what if we don't seed it with human knowledge? What if we just 100% from the beginning only use self-play instead? And when they did that, the game actually found much better moves near the beginning of the game that allowed it to reach an even higher level. In chess, there is a couple of tools out there. The first one is called Stockfish. And for a very long time, this was like the algorithm. Like if you go to like chess.com, which I spend time on, I'm not very good at it. But if you go here and then get started. Nope. Puzzles? Yeah. Start. Okay, if you're here, there is an analysis button somewhere. Get a hint. Sure. Okay, well, I can't find it. I really thought it was right there. Oh, here it is, the analysis button. All right, this analysis right here that goes through and calculates all these, if instead I had done something else, it will go and it will look up all of these different ways. Wow, that was funny. Whatever move I made did a bad thing. Oh, here it is, run report. And what you can see it doing is actually calculating all of the different moves that it thinks would be good. And this is using Stockfish under the hood. Right? So Stockfish is everywhere. It's in a lot of the best programs that are out there, although some of them are proprietary. You can go and you can download it. It's an open source project. And the way that it works is based on alpha beta pruning and minimax. And that's the whole thing. And then it has a very simplistic evaluation function that allows it to search really, really, really deep in a very short amount of time. Anyway, that's Stockfish. Stockfish was the best one for a very long time. And AlphaZero, they claim in 4 hours, was able to learn enough from self-play in order to beat Stockfish consistently. Like, I think they played it 100 games, and it won 78 of them and tied the rest, or something like that. But yeah. So not using human knowledge is like the big difference between the old version of AlphaGo Zero and this new version of just AlphaZero. Excuse me, that was the difference between AlphaGo and AlphaGo Zero. And then the difference between AlphaGo Zero and AlphaZero is that AlphaZero can now play 3 games. Okay. There we go. Okay. AlphaGo Zero estimates and optimizes the probability of winning, assuming binary win-loss outcomes. AlphaZero instead estimates and optimizes the expected outcome taking account of draws or potentially other outcomes. Okay. The rules of Go are invariant to rotation and reflection. This fact was exploited in AlphaGo and AlphaGo Zero in two ways. First, the training data was augmented by generating 8 symmetries. I believe they dropped that for this one. It was with Google infrastructure, yes, and TPUs, not like GPUs, like things that are specifically designed to solve this problem. Yes. All right. First, training data was augmented by generating 8 symmetries for each position. Second, during MCTS, that's Monte Carlo tree search, board positions were transformed using a randomly selected rotation or reflected before being evaluated by the network, so the Monte Carlo evaluation is averaged over different biases. The rules of chess and shogi are asymmetric, and in general, symmetries cannot be assumed. AlphaZero does not augment the training data and does not transform the board during MCTS. That's right. All right. In AlphaGo Zero, self-play games were generated by the best player from all previous iterations. After each iteration of training, in AlphaGo Zero, self-play games were generated by the best player from all previous iterations. After each iteration of training, the performance of the new player was measured against the best player. If it won by a margin of 55%, then it replaced the best player, and self-play games were subsequently generated by this new player. In contrast, AlphaZero simply maintains a single neural network that is updated continually rather than waiting for an iteration to complete. That's interesting. Okay. Self-play games are generated by using the latest parameters for this neural network, omitting the evaluation step and the selection of the best player. Sure. AlphaGo Zero tuned the hyperparameter of its search by Bayesian optimization. In AlphaZero, we reused the same hyperparameters for all games without game-specific tuning. The sole exception is the noise that is added to the prior policy to ensure exploration. This is scaled in proportion to the typical number of legal moves for that game type. So I would put a note by this. This is something that I'm going to have to look up because that doesn't actually make sense to me. Adding noise to the policy. I don't know if that's just like normal noise. It seems like it's explored here, so we'll go look that up. All right. Like AlphaGo Zero, the board state is encoded by spatial planes based only on the basic rules for each game. The actions are encoded by their spatial planes or a flat vector, again based only on the basic rules for each game. So this is interesting right here. There is a more recent version of this AlphaGo algorithm that plays not only these 3 games, but it also plays the Atari games that became famous when the DQN paper came out. And the way that works is they basically took these 3 games, Go, Shogi, and Chess, and they converted them into effectively video games. They just rendered the board as an image, and then they passed it in the same way. So we now have one medium, one screen size, that can take all of the information for all of these different games, and then it trained a single neural network to play all of the Atari games and these 3 games, and be good at all of them. But that's not what we're doing. We're still going to use something that takes in something similar, but is still very much our own. So we're going to come up with a representation for the board. And because in this game, in Othello, only the current board state matters, but in a game like chess, it's also important to know the moves that came before, because it can determine which moves are available. For instance, in chess, if you push a pawn 2 spaces forward at the beginning, your opponent can play an en passant in the case that they have another pawn in the correct position. So the previous move determines whether or not that en passant is a legal move or whether it's not. I don't think that's true for Othello, so we're not going to worry about it. We're just going to take the easiest possible thing that we can do. Okay. We applied the AlphaZero algorithm to chess, shogi, and also Go. Unless otherwise specified, the same algorithm settings, network architecture, and hyperparameters were used for all three games. We trained a separate instance of AlphaZero for each game. Okay, so I was wrong about that. In the new one, I am not wrong. They just converted it to an image, and the single network plays all the games. All right, training proceeded for 700,000 steps, mini batch sizes of 4,096, starting from randomly initialized parameters using 5,000 first generation TPUs. That's the Google hardware you're talking about. To generate self-play games, and 64 second generation TPUs to train the neural networks. That's a lot. Further details of the training procedure are provided in the methods. Figure 1 shows the performance. Figure 1 shows the performance of AlphaZero during self-play reinforcement learning as a function of training steps on an ELO scale. In chess, AlphaZero outperformed Stockfish after just 4 hours. In shogi, AlphaZero outperformed Elmo after less than 2 hours. And in Go, AlphaZero outperformed AlphaGo Lee after 8 hours. So let's put that into perspective. If it took 4 hours to reach 300k steps, okay, 300,000 divided by 4 is 75,000 steps. It's not. So mini batch sizes of 4,096. I'm curious here whether that means they played 4,096 games and that counts as a single step when updating the neural network, or whether they played 4,096 total moves. That's not super clear. We evaluated the fully trained instances, trained for 3 days, playing 100 game matches. AlphaZero and the previous AlphaGo Zero used a single machine with 4 TPUs. Stockfish and Elmo played at their strongest skill level using 64 threads and a hash size of 1 gigabyte. Okay, we're not worried about results. Can we get to details? No, that's it. That's all the details. Okay. That's all the details. And the details of the actual neural network, the parameters, theta. All right, instead of an alpha-beta search with domain-specific enhancements, AlphaZero uses a general-purpose Monte Carlo tree search algorithm. Each search consists of a series of simulated games of self-play that traverse a tree from root S to leaf. Each simulation proceeds selecting in each state S a move A with a low visit count, high move probability, and high value, averaged over the leaf states of simulations that selected A from S, according to the current neural network, F theta. The search returns a vector, pi, representing a probability distribution over moves, either proportionally or greedily with respect to visit counts at the root state. The parameters theta of the deep neural network and AlphaZero are trained by self-play reinforcement learning, starting from randomly initialized parameters. Games are played by selecting moves for both players by MCTS. At the end of the game, the terminal position, S state terminal, is scored according to the rules of the game to compute the game outcome. -1 for a loss, 0 for a draw, +1 for a win. The neural network parameters are updated so as to minimize the error between the predicted outcome value of state and the game outcome Z, to maximize the similarity of the policy vector to the search probabilities. Specifically, the parameters theta are adjusted by gradient descent on a loss function L that sums over mean squared error and cross entropy losses respectively. Okay, so they give you the actual loss function. For your network. So one of the parameters needs to be whatever predicted value came out. One of the parameters needs to be a value. And then you have the cross entropy of the policy. And then you have your regularization, which is just L2. Okay. All right. A little bit about how a neural network gets trained. And then we'll see if we can come up with an architecture that can take our board as input and then output what we need to output, which is a value and a policy. Okay. Okay, so for a neural network, normally you start off by just randomizing the weights of all of the connections to a somewhat small value, something very close to 0. Not 0, because then everything would just multiply out to 0, and you wouldn't actually update anything. So instead you set them all to be very small weights, and it just produces garbage at the beginning. Some output. And what you do is you take the output that it gives you and you subtract out the output. Well, subtracting is one way. You calculate a loss. There's a lot of different kinds of loss, but the most common one is to just subtract out the difference in whatever the prediction was versus whatever you know the answer to be. And then you back propagate that back through the network. And back propagating has a lot to do with taking the derivatives of the functions that you use to activate each one of the cells. And we won't get into that at the moment, because for the most part, PyTorch is going to take care of all of that for us, and we're not going to have to worry about it. What we do need to do is design a network with an architecture that can predict a single value and that can predict a policy over all legal moves. I'm not 100% sure how to do that. Okay, input-wise, we have 64 cells. It's an 8x8 grid, and each cell can have one of 3 states. It can either be blue, red, or empty. Is the policy related to exploration of algorithm? In a sense, yes. In a sense, yes. So when you're playing the game and you need to know what to do next, you have to choose one of your available moves. Since we don't know the actual outcome, since we can't evaluate all possible games, we come up with a policy. Is like it's like your uncle who thinks he's good at the game telling you, hey, when you see this, do this. When you see this, do this. Right? If you were playing poker, for instance, when you have, if you're playing Hold'em and you see that you have aces, he might be like, you raise. When you have a pocket pair, you raise. If you've got, 2 suited cards, you call. And if you've got 2 cards that are more than 4 values apart, you just fold. right? That's a policy. They just tell you what to do based on your situation. And that hopefully covers all situations. In this case, it will cover all situations because the board input has a consistent form and it's always going to spit out some answer. So what we're trying to do is we're trying to learn a better policy, right? So your uncle told you how to play this game and you're like, man, I still keep losing. I'm doing what you say, but I'm still losing. So what you do is you say, why am I losing when I follow, uncle's policy? And you say, oh, I'm going to change this. And so we update our policy. And now, whenever we see this, we play a different way, right? That's what it is. And that's how it helps guide the exploration. As far as the simulations, the answer is not really. The simulations are mostly controlled by the Monte Carlo tree search rules. And then we're going to use this function. What if the new policy is worse? Well, then hopefully you would learn that, right? You would say like, oh, I used to lose $3 every time I played. Now I'm losing $5 every time I play. So you go back to uncles and you say, all right, we're going to keep playing uncles because I wasn't losing nearly as much. And of course you have to try this a bunch of times. You have to lose that $5 enough times to be convinced that it is actually worse, right? Just because it does worse on the first try or because it does worse on the first 3 tries doesn't mean that it's not the best overall. It might just mean that, your chance of winning from this position is actually just quite bad. And so you're trying to figure out the difference that can sometimes be very small differences, but playing a different way can have longer lasting impacts. Does that make sense? Yes, it is possible that your new policy is worse. Ideally, that will not be the case. Because what we're going to do is we are very explicitly going to say, I played this and I lost, update the parameters of my network to play this a little bit less. And do something else. What it does else, who knows, but something else. There is another parameter. Okay, so there's 64 parameters that can have 3 states each. But there is another parameter that is whose turn it is. It is possible in this game to have the exact same state, but it to be the opposite person's turn. If I were to keep playing this out, notice that I can't play here. It's going to hold on to these until the very end, and it's probably going to get to a situation where I can no longer play. And I'm just going to play this out to show that to you. Like, it's going to get to the point where it's like, I'm going to play 3 times in a row. Nope, it didn't get there that time. Okay, it is possible to get to a point where you cannot play and you have to skip your turn and let the other person go again. And it's a good strategy to get your opponent into that position. So the learning will happen probabilistically more so than with back prop. So the learning is still guided by back prop. So let me see if I can draw a picture that makes a little more sense. Right. So we have the values, here's our state. And then we have this giant network of things, right? And then at the very end, it spits out a number or a vector of numbers, right? Every possible move in the game. There's 64 moves, so the output is going to be like 64 values, 64 floats. Okay, 64 of these. And this is just a vector, meaning it's literally just an array, 64 floats. Okay? ... Bunch of these. And then this is going to say that when you're in this position and you play this move, what happened was we won or we lost. yeah, we won or we lost. In the case that we won, this is harder than I thought. So, yeah, you have a distribution of moves. How do policy gradients work? And then you have a value of basically trying to say I'm gonna have to look this up more. Okay, so let's imagine that you were instead of printing or instead of outputting move probabilities over all the moves, instead you were just outputting one number, and we'll come back to this. Instead, you're just going to output one number, and this is like a 0.37, right? That's the number that got output. But when we played this game, we actually lost, right? So we had a -1 score. So what we would do is we would take this value minus this value, and that's how far off we are. And so what we would do is say, what direction we want to move in. We have a -1. We have a -1 minus. These get subtracted one way or the other. It does matter. It's just not coming to me off the top of my head. And then you find the difference between these, which is like a difference of 1.37. And then you're going to take this number. This is how far off we are. And then you're going to start backpropping that through here. And as it backprops, it updates all of the weights in here. And the next time that we run that same state through the network again, it might be like 0.26, right? It's closer. We don't jump all the way to the conclusion to say that this is always the correct answer, because the very next time we play this, we might actually win. Like, if we see this state again, we might win in that state. And this is very true of all of the starting states, right? Like, the first few moves, if the game split of wins and losses is like 55% for the first player and 45% for the player who goes second, then those early moves, like, you're going to see wins and losses for both of them. Anytime you get into a terminal position, it's going to be guaranteed that, like, the score will always be the same, and it will learn those very quickly. But when you see the same state and sometimes you win and sometimes you lost, we only want to move a little bit in that direction, because if we moved all the way, then we would just keep bouncing back and forth, and we would never, like, settle on a value and say, like, okay, this is what I think, you know, is your chance of winning. Instead, we would either say, if you play this, you're going to win. If you play this, you're going to lose. So instead, we discount that, and it's called the learning rate. And your learning rate starts out usually very small, like on the order of like 0.01 or maybe less. And there are tools that you can use for that called optimizers that do a bunch of whatever they do. I'm not entirely sure. The simplest optimizer is literally this, where you just subtract the values and then you multiply it times a small learning rate. And that's how much you update as you do your back propagation. But there are other tools like RMS prop and an atom optimizer. There's a bunch of different ones. But yeah, so in this case, we have predicted something. And I think what we do is we need to have a second network that actually predicts what we expect to be the output. That's my understanding. And that would be called a target network, and this would be your learning network. So your target network says, if I'm in this state, I expect to win this much based off of each of these moves that I make. And Instead, this was what I got as a move distribution. I'm going to have to look that up. Like I said, I just don't know. Policy gradients is what this is going to be about. Policy gradients. Like you directly learn the policy. Policy gradient algorithms. Can you go there? Okay, what is a policy gradient? Policy gradient is an approach to solve reinforcement learning problems. If you haven't looked into the field of reinforcement learning, a long peek into this. Okay. The goal of reinforcement learning is to find an optimal behavior strategy for the agent to obtain optimal rewards. The policy gradient methods target at modeling and optimizing the policy directly. The policy is usually modeled with a parameterized function. The value of the reward objective function depends on this policy, and then various algorithms can be applied to optimize theta for the best reward. The reward function is defined as okay, this is a value. Okay. This is saying right here, if you follow the policy and this is the optimal value, then your total expectation is this for each state? Sure. The stationary distribution of Markov chain for the optimal policy. For simplicity, the theta parameter would be omitted for the policy. Pi, when the policy is present in the subscript of other functions. Okay, so that's just terminology. The policy gradient theorem. Computing the gradient is tricky because it depends on both the action selection and the stationary distribution of states following the target selection behavior. Given that the environment is generally unknown, it is difficult to estimate the effect on the state distribution by a policy update. Luckily, the policy gradient theorem comes to save the world. Woohoo! It provides a nice reformation of the derivative of the objective function to not involve the derivative of the state distribution and simplify the gradient computation a lot. We're going to skip the proof. Reinforce. Relies on an estimated return by Monte Carlo methods using episode samples to update the policy parameter theta. I still don't understand it. I don't know how you get the values of what the policy should be. How do you get the values of what the policy should be? I don't know. Let's do the old policy gradient example. My clicking ability is diminished today. Aren't you going to ask me if I want to sign up? Introduction, reinforcement learning. Okay. Background and definitions. Okay. Policy gradients. The objective of a reinforcement learning agent is to maximize the expected reward when following a policy pi. I thought there would be agents playing each other and evaluating their position value, and then compare each other evaluations at the end of the match to see which was wrong. Maybe is my answer. Like, conceptually, it's telling us that the policy is output, and we're calculating the cross entropy of the policy. This is simply saying take the value that we predicted minus the actual value and square it. It's this policy one right here that I'm having trouble with. Like, what is policy? To the search probabilities. Maximize the similarity of the policy vector to the search probabilities. Oh, so this is actually coming from the tree search. Okay, so at this state, for each additional move that we made afterward, we have the results of the Monte Carlo tree search. And so what we're trying to do is we're trying to train the network against what Monte Carlo tree search decided was the best move for each of them. Okay, that makes total sense now. Does that make sense to y'all? So in Monte Carlo tree search, we're in a given state. We expand all of the possible next states that come after it. And so then we do the tree search, right? From there. And we end up with a distribution of how often each one of these different moves was played. And we treat that as the correct value that we're trying to get to. For every policy t, there is a corresponding search probability t, and you're taking their dot product. The dot product of the log of the truth. Yes. Why the log? I don't know the answer to that. Maybe that's just how cross entropy works. Entropy. In information theory, the cross entropy between two probability distributions, P and Q, over the same underlying sets. Oh, let me make this bigger for y'all. Over the same underlying set of events measures the average number of bits needed to identify an event drawn from a set if a coding scheme used under the set is optimized for an estimated probability distribution Q rather than the true probability distribution P. What is E? Okay. So yes, it's the dot product of the output policy and the log of the real policy. Okay. And then this is just L2 regularization, which you literally just take all the parameters, square them, and add the values. Okay. All right. Let's think about how we can design something for this then. So we have 64 locations that can have yeah. It's hard. I still struggle with all these things. Blue won the game. Like I said, I've never beaten it, but in this case I wasn't playing it for real. But yeah, like at the end, when it can do hundreds of thousands, like you don't have a chance of beating it. If it's gonna win, it's gonna win because it's effectively evaluating every possibility. Okay. All right, so there are 64, and you need red, blue. So I think we're going to use -1. We're going to use 1 for the first player. Is that helpful? We can basically input this as like -64 values twice, 128, 129 values. We could do this as 129 values. Just binary values, 1 or 0. That determines your state. Which seems right to me, I think. So your input's going to be 129 values. The first 128 of them, no, I'm sorry, the first 64 of them are going to be a 1 or a 0 for each possible board cell, whether or not there is a red in that cell. The second 64 is a 1 or a 0 for each possible cell where there is a blue. And the last one determines whose turn it is, player 1 or player 2, which will denote by, I suppose, a 1 and a 0. So again, binary. Although maybe we don't need that 129th value. Maybe we can just do 128 values. Because in a given position, would it always be the same person's turn if that person can move? Is it possible to get into a situation where the same board can be 2 different players' turns? Or will the skipping aspect force it to be one player's turn or the other? I feel like in chess, Maybe if we just double the board. Maybe if we just double the board here and we show the last state and the current state, it solves that problem. And since if you ever wanted to like augment this to play any other game, you'd basically have to do that as well. I'm not entirely sure if we should do that. That's a lot more input parameters, and I want to keep this super compact, if at all possible. I guess what you do is you just try it, and then you just see what happens. Right? Like if it's in this state, it's always player 1's turn. This will never be player 2. If it's in this state, it's always player 2's turn. Now it's all, back to player 1's turn. And no matter what, it will always be... Yeah, I think that's how we should do it. I think we're not going to worry about whether or not... I don't think we're going to explicitly encode whose turn it is. I think it will always just be known from the current state. I think so. Okay. So we want 128 inputs. Let's go ahead and draw this. All right. We want 1 by 128. I am not good at this. Goodness me. One by 128. Okay. Now we need I wonder if doing this in a convolutional way would be helpful. I don't know. Let's just choose the easiest possible thing. I guess make this network. You can do it 2 by 64 and send it to the neural network to assume the first column is his to play. Solid choice. That's very smart. 2 by 64. Okay, so whoever's turn it is, that player's pieces go at the beginning. And then whoever's turn it is not, those pieces go at the end. Okay, that makes total sense. Okay, I guess as far as a network goes, we're just going to define something. I want it to widen, and then I want it to shrink down. And at the output, we need another... On the output, we need 64. Okay? So let's put something like... And to make it, deep, let's just do something really rudimentary to begin with. Okay. So this is going to be... let's say we're going to do 512 here. And then 128 again. And then 64. And then we also need this needs 65 outputs, right? Because we have to predict the value as well. That value. Okay, so we need 65 outputs. I guess another way to represent that would be like 64. And then one. Okay, that is Z. And this is pi. No. This is awful. Pi symbol. There we go. Okay. I mean, let's try it. Anaconda. Sure. Environments, learn PyTorch. And then we're going to go with ICD experimental, learn PyTorch, Jupyter Lab. All right, have a good one. Thanks for stopping by. Okay, copy this. Okay, now let's add in a new one called rename, called Reversey. Okay. Import torch. And then what do we want to do? We want to create a neural network. That was in module 3. Basically just going to copy this. Then we have a network, and we're going to define this network. Only it's not going to be convolutional. Well, that's one thing we could do. We could do a convolutional and just have 2 channels. 64, that's the 2 by 64. Sure. We're going to change as little about this as possible. Okay. Two. 1 input image channel. 2. We're going to output. It's an 8 by 8. So the output of this is going to be like a 3 by 3. That almost doesn't seem valuable. You know what? Let's just do linear layers for the whole thing. Okay. On the input, we're going to have 2 times 64, and we're going to output 512, we said. Then we're going to have 512 as the input, and we're going to output 128. And then we're going to output 128 to 64. Okay, max pooling over a 2 by 2 window. No. We're going to jump right to here. Okay. Okay. We're going to use these rectified linear unit activations. This is really straightforward. No, not quite. We also need the value. So this is going to be a policy layer, and this is going to be value layer, and this is going to spit out one value. And then, hey, thanks so much for the follow. And then I want to say this is going to be the policy. And maybe I do need it to be 65. I don't know if you can just like explicitly run the same thing twice. I would want to return both things, but it's going to expect one back. Maybe we just make it 65. I'll put a little note here. Can we do this with 2 separate calculations? output layer. Okay. And then we can just leave that as X. Let's see if that actually works. I also wonder if I even need this. I'm not sure. I'm gonna say I don't need that. Okay, let's see if this works. All right. Okay. We have a network. Now, let's put some values into it and then see if this is actually gonna print out something useful. Right. What we want is a bunch of ones and zeros. So let's put the first one in there. Starting position equals import. Oh, well, I guess I can do it like this. Starting position equals torch dot tensor. Uh, 2 by 64. Does that work? Okay. And I want to say there's a way to zero it out, which we learned in module 1. Torch.empty. Nope. Torch.zero. Zeros. Yay, there we go. Okay. Okay, now this thing will actually help me because this is cell 0. If we refresh, we can see the starting position. So 27, 28, 35, 36. Okay, 27 and 35. 27. Starting position. Uh, 25. 0. 25. No, 27 equals 1. 36 and this is 1 and 1 and 28 and 35. Okay, There's our 1, there's our 1, there's our 1, there's our 1. Perfect. Okay, so that is our starting position. And now, if it spits something out, which we just call net, and then we get the output. Starting position. Okay, what are we complaining about? Size mismatch. Okay, so we do need this. No, we don't. Yes, we do. 2 by 64, 128 by 512. That's why it does that. Okay, we do need this resizing. And then we have this one. 2 by 64. I guess just 1 by 128. Or is it rand? What is rand in? Give me contextual help. Torch.rand in. Torch.rand in gives you the size that you care about. Okay. So 1, 1. One, 1, 32, 32. I think the first layer is expecting 128 instead of 2 by 64. I think that might be part of it. Oh yeah, well I screwed that up too. Okay, I want to do it like this. I want to add these ones in right here. Hey, thank you so much for the follow. I really appreciate that. And then let's just kind of comment these out for the time being. So one of the things that I remember reading in that tutorial was that when you pass in input, it expects that you're passing in a batch. So you need to format it as if it were a batch. Hey, thanks. I really appreciate that. So in this case, we would then say, what, 0? Maybe it's just 1. Okay, let's try this. No. Has no object FC3. Okay, well, we got further. Yeah, now let's figure out how to mod that. How do I mod? There we go. Okay. Now we named this FC3. We're gonna rebuild the network. Gonna rebuild this. Gonna try this one more time. Hey, what's up? Print output. Oh, yes. Okay. Okay. All right, so now we have some values outputted. And now what we need to do is tell it to move toward certain values. So we want a target. Equals torch dot zeros of 1 by 65. And then we want target of 0.64 equal to 1. So that's going to be our value. And then we want all of the other ones to be basically 25. Where is it? We want 20, 29, 34, 43. Okay, 20, 29. Ah. 0.25. 20, 29. I'll explain why I'm putting these very hard-coded numbers in here in just a second. And then 34 and 43. 34 and 43. Okay, I'm putting these 0.25, these are the move probabilities that I want to optimize towards. And the way that this works is if you rotate this board, all of these moves are exactly the same move. There's just one move, and so the chance that any given one of them is better than the others is 0 for the most part. So we just want them to all be 25. That's what we want them to move towards. And then we're going to say that this game resulted in a win for the first player. Okay, so that'll give us a target. Now, we need to go back to here where we actually trained this thing. And we want to say out.backward net.zero gradient out.back. I think there's a better example of this. Oh yeah, we want to do all of this. We know we want the cross entropy. How do we do cross entropy? Only over 24 of them. So this is why I wanted to do the separate thing right here. This is why I wanted to do it this way, because we need to calculate cross entropy over just this. And we need to calculate maybe we can still do this. Okay. I'm lost. What am I looking for? Okay. We want torch.optim. Okay. I'm just going to do atom. Okay, atom is a thing. Net.parameters. Learning rate, super small. I think we're going to get rid of the momentum. Okay. And then okay. And then we want to do 4. And range 1000. Okay. Zero out the gradients. Output equals net inputs criterion equals outputs 0 to 64 and okay, we're going to do target policy equals target of 0 to 64 and target value equals target of 64. Okay, and then we're going to put this in here as target policy. No. As outputs? Yeah. Yeah. And then target policy. Plus hey, thanks so much for the follow. And then this is going right back to basically copying this. So we want to do whatever it spits out. No, the real value minus whatever it spits out squared. The real value, target value, minus outputs 64. And then square that. Is that how you do it? Python square. No, PyTorch square. Torch. Okay, squared. So we're going to do it like this. And then we're going to ignore regularization for now. We'll come back to that. I want to see if this will actually work. And then we're going to do I mod. Okay. Reporting steps equals 100. Reporting steps minus 1. Divided by reporting steps. And let's do 5 because I just don't know how small it's going to be. It's probably going to be pretty high. Okay. Okay, we're just going to try it. I have no idea if this is going to work or not. Of course it didn't. Index 64 is out of bounds for dimension 0 with size 1. Oh. Zero. 0. I think. Index 64. Okay, let's just print outputs. Line 2. Oh. Oh. Yeah, thanks. 0. I guess I don't really need it to be like that. Okay. Inputs not defined. Starting position. Dimension out of range. Expected to be in range of -1, 0, but got 1. I guess. We don't need to output. Whoa. Okay. It looks like we do need to index this first one. Although this looks like it's totally divisible by 4. 1, 2, 3, 4, 5. Oh no, divisible by 5. Okay, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65. Okay, so that's... This gives you a tensor, and I think maybe we have to actually get the value out of it. How do you do that? That was in module 1. If it's just a single value, target value is 1 dimension. Right, I want to just subtract the value at this. Target value. Expected input batch size. To match the batch size, 64. Where is that happening? What if we break this up into different lines? You know what? I'm going to guess we can do this. It doesn't care what it returns. This is my guess. So this is going to be policy equals self dot policy layer of x. And then here is going to be value. And this is going to be value layer of x. And we're going to return policy and value as a tuple. And then when we run this, we're going to get a tuple back. Yes, okay, we got a tuple back. That's exactly what we wanted. Now, when we run this, we can say, not outputs, but we can say policy and value. And then we can just say policy and value. And then I think, no, I still think you're correct here that this needs to actually be wrapped up. Like this needs to be a tensor. So we want, let's print out target policy. I just want to see if it's a tensor is what I'm looking for. And it is a tensor. Okay. So that is what I want. Only I do need to add in dot view 1 minus 1. I want to, I think that's how you do that. Yes. One minus 1. And then let's just print target policy one more time. Okay, so I did add in the extra. Where is it dying? Alright, it's still dying. Expected object of scalar type long, but got scalar type float for argument number 2. What? Print policy value. Print target policy, target value. Float. I'm a little stuck here. I don't quite understand what it's doing. It's got the same shape now. You can see right here and right here, these have the same shape. That's what I'm going for. Let's get a PyTorch example with regularization. Regularization example. Oh, it's dot sum. Right. Okay. I'm pretty sure what's happening here is, yes, they have the same shape, but the loss needs to be a single value, right? So this cross entropy calculation is returning a single value. It's not returning the cross entropy for each and every example. And this is doing an element-wise subtraction, an element-wise squaring, and then I need to do a sum over those. That's my guess. Expected object of type scalar, type long, but got scalar type float for argument number 2, target, and call to NLL. Okay, you know what we're going to do? We're going to just separate them out and figure out which one is the problem. Okay, it's that one. Expected scalar type long. Okay. Let's look at the cross entropy loss. Labels. And the outputs. I'm not quite understanding that. Let's do one of these and just print it out and see what the shape is. Or you just do what you always do and Google the error. The output layer should have the number of classes as out features. Currently, your output layer returns 1 neuron, which corresponds to class 0. For a binary use case, this should work. Batch size 5, number of classes 2, in features 10. Linear of in features to number of classes, cross entropy loss. Target. Why should I was creating the target tensor and passing float as D type. What is torch.long? Is that an integer? Torch.long. What in the hell? Why does it want a long? That doesn't make any sense. Expected object of scalar type long but got scalar type float for argument number 2. Huh? I don't understand. In features. Torch.randin batch size in features. Why on earth does it want it to be long? You can try putting 1.0 as input, maybe? Oh, yeah, okay, let's try that. You mean right here? Huh. What in the... Nope, the starting position. Yeah, what is it? D type equals torch.float. And right here, D type equals torch.float. Oh. Float. Okay. Float. What in the hell? The D type to be torch.long, but the error still pops out. Seems boxes 1 is passed as a long tensor, while boxes 2 is a float tensor. Why there is boxes 1 and boxes 2? If I make the target long, let's look at the output, right? Let's look at the output. Like that. Okay, those are floats. So I guess we'll just try that and see. Target policy.long print target policy.long. That's not right. That gets rid of my targets. It makes them all 0. And then it still errors out. Okay, so the long thing, that's not correct. Let's print these out and these out. Wow. It has the same shape. No, it doesn't. Look at that. It does not. Okay, this one right here has 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's 64. 1, 2, 3, 4, 5, 6, 7, 8, 9, 18. Oh well. 1, 2, 3, 4, 5, 6, 7. 7 times 9 is 63, 64. I guess more directly we could just call shape. Policy.shape target policy.shape. Torch.size. Object is not callable. Size. Sure, size. One by 64, 1 by 64. Wild. Okay. I don't know what the problem is here. Do we use cross entropy in this one? We do use cross entropy. All right, I'm going to run this. And then right here, I'm actually going to print out print inputs.size. No, outputs.size. Labels.size. Print. We keep doing this. Print outputs.dtype and labels.dtype. Wild. It is a long. What the hell? Outputs.size is 410. Oh. Okay, okay, okay. So the labels are a number 1 through 10. Let's just print. No. Let's just do labels. I'm going to guess that the labels are like the number 3, the number 7, the number 5. And this cross entropy loss is actually doing whatever expansion it needs to. Yeah. Okay. Okay. Wow. I don't like that. I don't want it to be like that. Let's do nn.cross entropy torch nn.cross entropy loss. Okay, so this assumes softmax. Which is not what we want. Okay. I don't need that anymore. I don't need that anymore. I don't need that. Come back to that whenever. I don't need that. The true distribution. Oh. It is doing the softmax, which is kind of crap. Instead of putting 0.25 in there, I could put the actual numbers that would be coming from the number of explorations in the tree. So like 250, 250, 250. Which would make the log make a whole lot more sense. So how the hell then do I get away from the softmax? Because I don't want it to be that. Multi-label soft margin loss. Okay, let's go cross obtaining log probabilities in a neural network is easily achieved by adding a log softmax layer in the last layer of your network. It's not binary cross entropy. That's not what we want. What's that one? Cross entropy loss. If provided, the optional argument weight should be a 1D tensor assigning weight to each of the classes. This is particularly useful when you have an unbalanced training set. The input is expected to contain raw, unnormalized scores for each class. Input has to be a tensor of size either math or mini batch C D1 D2 D. Okay. Okay, this actually makes more sense now. I think we can overcome this. So our tensor is going to be long and we're going to put a 1 in there. And we're going to put 250. All right, so we ran 10,000 simulations. All right, I'm starting to think this is going to make more sense. We ran 10,000 simulations, and these 4 came out to be equal. To use BCE. I don't know what BCE is. Hey, keeping track of this account. Well, welcome to the class. BCE. I saw that as we were going through. I don't know what it is. Creates a criterion that measures the binary cross entropy between the target and output. I don't know. I'm going off of the paper. Specifically are adjusted by gradient descent on a loss function L that sums over the mean squared error and the cross entropy. Notice this is a subtraction also. That's pretty wild, huh? That sums over the mean squared error and the cross entropy. Let's go ahead and draw that. How it's supposed to go, I suppose. I don't know if this is going to work or not. just trying it is my answer. That's my answer. I don't know. Our problem is kind of yes, no problem. That the piece should be there or not. So I want it to give me a probability of what my win chances are for each one of my places that I can play. I want this to be a probability distribution. I'm going to just see if this works. I don't know if this is going to work. I'm just going to try it. Okay. And now I feel like there was one more thing missing. Nope, I don't know. Oh, did I actually... Multi-target not supported. Multi-target not supported. I don't know. Did I do this correctly? Target policy. I think I need to do one more. Multi-target not supported. Criterion, cross entropy. Cross entropy loss does not expect a one-hotted encoded vector as the target, but class indices. The input is expected to contain scores for each class. This criterion expects a class index 0 to C-1 as the target for each value of a 1D tensor. Well, how the hell do you do a cross entropy of... How do you do... What the F? Cross entropy without class labels. PyTorch cross entropy. What is the thing that we're doing? Gradient policy gradient. Saved log probabilities. Rewards. Affine, dropout. ReLU, action scores. Self.affine2, softmax. Policy. Policy loss. Torch.tensor. Log probability. Reward. All right. I think it's time for a break. Been kind of grinding at this for a while. Feel like we had some amount of progress. Gonna figure out how to get this cross entropy calculated. Gonna figure out how to get this cross entropy calculated. And then that's it. Probably going to work on that later. Okay. I would really like to thank everybody for stopping by today. Thank you for the follows. Pac-Man Jr., Ash K, 1994S, Eigenfunk, JB Perry, keeping track of this account. And thank you for the raid, Clarkio, and thank you for the 100 bits Power Stomp. I really appreciate that. I will be back tomorrow around, I don't know, maybe 12:30 or 1. And yeah, thanks for hanging out. Junk food is bad. I do appreciate that. Thanks for hanging out. Thanks for trying to help as well. I get stuck on this stuff all the time. And I really appreciate it. So thank you. And yeah, I'll see y'all tomorrow. Y'all have a good one.